Okay, more questions? No. Okay, so if not, let's move on to more general parametric equations. So I hope you've seen here that parametric equations are a great way to think about a line in space. They're also a great way to think about actually any curve, any trajectory that can be traced maybe by a moving point. So more generally, we can use parametric equations for arbitrary motions in the plane or in space. So let's look at an example. Let's take, so it's a famous curve called the cycloid, and the cycloid is something that you can actually see sometimes at night when people are biking if they have something that reflects light on their wheel. So let me explain what's the definition of a cycloid. So I should say I've seen a lecture where actually the professor had a volunteer on a unicycle to demonstrate how that works, but I didn't arrange for that. So instead I will explain it to you using more conventional means. So let's say that we have a wheel that's rolling on a horizontal ground. And as it's running, of course, it's going to turn. So it's going to move forward to a new position. And now let's imagine that we have a point that's been painted red on the circumference of the wheel. And initially that point is here. Okay? So as the wheel starts rotating, well, of course, it moves forward and it turns on itself. So that point starts falling back behind the point of contact, because the wheel is rotating at the same time as it's moving forward. And so the cycloid is the trajectory of this moving point. Okay, so the cycloid is obtained by considering, so we have a wheel, let's say of radius A. Okay, so this height here is A, rolling on the floor, which is the x-axis. And let's, and we have a point P that's painted on the wheel. Initially, it's at the origin. But of course, as time goes by, it moves on the wheel. So P is a point on the rim of the wheel, and it starts at the origin. So the question is, what happens? In particular, can we find the position of this point, x of t, y of t, as a function of time? Okay. So here's the reason why I have this computer. So I'm not sure if it will be very easy to visualize, but so we have a wheel. Oh, that's not very well, I hope you can vaguely see that there's a circle that's moving. The wheel is green here. And as, there's a radius that's been painted blue on it, and that radius rotates along the wheel as the wheel is moving forward. So now let's try to paint actually the trajectory of the point. Okay, so that's what a cycloid looks like. Okay, so the cycloid, well, I guess it doesn't quite look like what I've drawn. It looks like it goes a bit higher up. But it will be the trajectory of this red point. And see, it hits the bottom once in a while. It forms these arches because, well, when the wheel has rotated by a full turn, then you're basically back at the same situation, except a bit further along the road. Okay, so if we do it once more, see, the point now is at the top, and now it's at the bottom, and then we start again, it's at the top, and then again at the bottom. Okay. No. Okay, so the question that we want to answer is, what is the position x of t, y of t, of the point P? Okay, so actually, I'm writing x of t, y of t. That means that I have, maybe I'm expressing the position in terms of time. Let's see, is time going to be a good thing to do? Well, certainly the position changes over time. But does it actually matter how fast the wheel is rolling? No, because, I can just play the motion in fast forward. The wheel will be going faster, but the trajectory is still the same. So in fact, time is not the most relevant thing here. What matters to us more is how far the wheel has gone. So we could use as a parameter, for example, the distance by which the wheel has moved. Or we can do even better, because we see that really the most complicated thing that happens here is really the rotation. So maybe we should actually use the angle by which the wheel has turned to parameterize the motion. Okay, so there's various choices, and actually you can choose whichever one you prefer. But I think here we'll get the simplest answer if we parameterize things by the angle. So in fact, instead of t, I will be using, let's call theta, as a function of the angle